Another reason to study quantum query complexity is that we can actually show lower bounds in this model. Okay, so we can show that some problems are difficult for quantum algorithms in terms of the number of queries that the algorithm needs to make to compute the function. So I want to talk about how we show lower bounds on quantum query complexity in this segment. And the example that we're going to focus on is the OR function. Okay, so this is a total Boolean function, from 0, 1 to the n to 0, 1, and it evaluates to 1 if and only if the input has at least 1, 1. Okay, so it only evaluates to 0 on the all 0 string. And we know that any quantum algorithm which computes the OR function has to make at least a constant times square root of n many queries to the oracle. Okay? And one really interesting consequence of this result is that it means that a quantum algorithm cannot just, in a black box kind of generic way, search through all possible 2 to the n assignments to a formula on n variables to find a satisfying assignment. Okay, so there's not just kind of this generic black box way for a quantum algorithm to efficiently solve the satisfiability problem. Okay, so there's two main techniques for showing quantum query complexity lower bounds. They are the polynomial method and the adversary method. And we're going to look at both of these methods and see how each of them can show a lower bound, this lower bound of square root of n, on the quantum query complexity of the OR function. Okay, so I'm going to be talking about different representations of Boolean functions for this segment. Okay, so for the polynomial method especially, it is more convenient to consider a representation of the function over -1 plus 1 instead of 0, 1. Okay, so we're actually going to consider functions from -1 plus 1 to the n to -1 plus 1. And given a function f, we can easily convert it into kind of an analogous or equivalent function over -1 plus 1. And usually the way that we do that is we map 0 to 1 and 1 to -1. Okay, so the definition of the analogous function corresponding to f, I'm going to call it f plus minus. It's just f plus minus of input 1 minus 2 times x is equal to 1 minus 2 times f of x. Okay, so this little function inside here, 1 minus 2x, it just maps 0 to 1 and 1 to -1. Okay, so for any function f, we can consider its kind of signed version, f plus minus, just by doing this little transformation here. And this transformation doesn't really change, any parameters of the function that we're interested in. So any of the complexity measures of the function that we're interested in. Okay, so we're going to kind of freely switch between these two representations. Okay, so now let's start by talking about the polynomial method. And just as kind of a warm-up to put your brain in the right frame of mind, consider this question. What is the solution to this system of linear equations? Okay, so you could, just start doing Gaussian elimination on this system, right, to figure out the answer. Or, you might notice that this matrix here is pretty special, right? The columns are orthogonal to each other. And in fact, this matrix is just the Hadamard matrix tensored with itself with a different normalization. Okay, so since we actually know the inverse of the Hadamard matrix, we can just multiply by the inverse here. okay, and easily solve this system of linear equations. Okay, so here we have this H tensor 2 with a different normalization, and its inverse is going to be this matrix here. Okay, so it's 1/4 times the same thing that we have up here. Okay, so we can just multiply by the inverse to solve the system of linear equations, and we get the following solution. Okay, so now let's see what this has to do with polynomials. Okay, so as I said before, we're actually going to work with the sign version of functions. Okay, so we're going to consider functions from -1 + 1 to the n to -1 + 1. And typically we think of -1 as representing true. A nice thing about using this -1 + 1 representation is that it makes representing parity functions very easy. Okay, so let's say I'm interested in the function which outputs -1 if and only if the number of -1s in the input is odd. Okay, so here I've written out this function on two bits. Okay, and you can see that the output is just the product of the input bits. Okay, so in this case, it's easy to express this function, parity of 2 bits, as a polynomial, right? So as a polynomial, it is just x1 times x2. And this is actually what's called a multilinear polynomial. Okay, and that just means that the highest power of any variable is 1. Okay, so this actually gives a function that is linear in each variable separately. Okay, so think about this as a function of any one argument and holding all the other variables fixed. That is a linear function. Okay, so we can define parity functions more generally, okay, over any subset of the input variables S. Okay, so I'm going to let chi S be this function which just takes the parity, so outputs -1 if and only if the number of -1s in the input X restricted to the set S is odd. Okay, so again, this function is very simple to represent by a polynomial. The polynomial is just the product over I and S of xi. So we've actually already worked with these parity functions a lot. They are just the columns of the Hadamard matrix. Okay, so if here I have all 2-bit strings, and I think of this as bit 1 and this as bit 2, okay, then if I want to know the parity, let's look at this one. Okay, so the parity of these 2 bits. So in this case, there's no 1s, so it's 1. In this case, the number of 1s is odd, so we output -1, again -1, and here 1. Okay, and you can see that every column of this matrix corresponds to a parity function on a subset of the input bits. Okay, and this is just an unnormalized Hadamard matrix. Okay, so a consequence of that is that every Boolean function can be uniquely expressed as a linear combination of these parity functions, right? Because in general, these parity functions are always going to be the columns of a Hadamard matrix. We know that the Hadamard matrix is invertible. So, no matter what right-hand side we have, we have some Hadamard matrix here, and we want to express some target function f as a linear combination of the columns of this matrix. Well, we know that the system of linear equations has a solution, right? Because this matrix is invertible. Okay. So moreover, this tells us that this representation of f as a linear combination of parity functions, it's going to be unique, right? Because this system of linear equations has a unique solution because, again, this matrix is always invertible. Okay, so to make this concrete, let's look at an example. So say that the function that we're interested in is the AND function. So the AND function in this -1 + 1 representation looks as follows. So it maps to -1 if and only if both of the input bits are true, which in this case means both the input bits are -1. Okay, so how can we express this function as a polynomial, as a linear combination of these parity functions? Okay, so we can just look at the truth table of the AND function, and we want to express that as a linear combination of the parity function. So I claim that this is how we can express the AND function as a linear combination of the parity functions. Okay, so here I have the truth table of the AND function, and here I have the truth table of the constant 1 function, right? And the truth table of the function which just returns x1. So we see that's the function that just returns x1 is 1, 1, has truth table 1, 1, -1, -1. So that's here, right? This is x1. And now the function x2, let's see, so x2 is 1, -1, 1, -1. So that's this function here. That's the truth table of the x2 function. And finally, x1 times x2 has this truth table. Okay, so you can just work this out, that this equation is true, and this is how you can express the AND function as a linear combination of these parity functions. And again, how did we arrive at this? Well, it's just solving a system of linear equations with an unnormalized Hadamard matrix. Okay, so here again I just have a matrix whose columns are the truth tables of these 4 parity functions, right? The constant 1 function, the function x1, x2, and the function x1 times x2. So I want to solve this linear equation. If I solve this linear equation, then these coefficients z1 through z4 will tell me how to express the AND function as a linear combination of these parity functions. And we can solve this simply because we know the inverse of this matrix, right? So the inverse of this matrix is again a Hadamard matrix, up to some different normalization, and so we can just multiply by the inverse to get our coefficients here. Okay. So again, this tells us that the AND function can be written as 1/2 times the constant 1 function plus the function x2 plus the function x1 minus x1 times x2. And this procedure is completely general. Okay, so for a general f, right, what are the Fourier coefficients of f? Well, those are just the coefficients that tell us how to express f in this different basis, in this basis of parity functions. Okay, so f hat s, that's the Fourier coefficient of f corresponding to subset s. And these Fourier coefficients just tell us how to express f in terms of these parity functions chi s. Okay, and so the Fourier coefficient corresponding to set s, it's just going to be the overlap of f with this parity function, up to some normalization. And this is what we just saw in the example of the previous slide. So basically, to get all these Fourier coefficients, you can just multiply f by the Hadamard matrix of the appropriate size, and with this appropriate normalization. Okay, So basically, we just multiply f by a Hadamard matrix, with a different normalization, and that gives us this vector of all Fourier coefficients. Okay, so now that we have the Fourier coefficients of f, we can define its polynomial degree. And the polynomial degree of f is just the maximum size of a subset S such that the Fourier coefficient of f corresponding to S is non-zero. Okay, so in the case of the n function here, the Fourier coefficient corresponding to subset 1, 2 is non-zero, right? It has value -1. So this n function has degree 2, okay? And we can similarly express the majority of 3 function as a polynomial. Okay, its representation as a polynomial looks as the following, and this has degree 3, okay, because it has this term x1 times x2 times x3. Okay, so we're actually going to be more interested in showing lower bounds on bounded error quantum query complexity, right? So where the algorithm can have an error with some small probability. And for that, we're going to want to talk about not polynomials which exactly represent a function, but just polynomials that approximately represent a function, okay? And for this, I'm going to change the notation a little bit. So I'm going to think about the range of the function as 0, 1 instead of -1 plus 1. Okay, so again, this is just a simple transformation, and this change does not affect the quantities that we're interested in. In particular, it does not affect the degree. Okay, so now I'm thinking about functions where the domain is -1 plus 1 to the n, but the range is just 0, 1. Okay, so now let's define the approximate polynomial degree of a function. So first, what does it mean for a polynomial to epsilon approximate a Boolean function? Well, it just means that on the entire cube, so for all x and -1 plus 1 to the n, the value of f of x and the value of p of x, they differ by at most epsilon. Okay, so that's what we mean by epsilon approximating, by approximating a function with epsilon error. Okay, so the polynomial always differs by f of x, on the domain by at most epsilon. Now, the approximate degree of f is the minimum degree of an epsilon error approximating polynomial for f. Okay, and we denote this as the degree subscript epsilon. Okay, so this can actually be smaller than the degree of f. Okay, so we can see a small example here. So if we go back to our AND function and just consider this polynomial, so now I no longer have a degree 2 term. Okay, so this polynomial is just 1/3 times quantity 1 minus x1 minus x2. Okay, and now if you look at the values of this polynomial on -1, 1 on 2 bits here, you see that it's always within 1/3 of what it should be. Okay, so this is actually a 1/3 error approximating polynomial for the AND function, and it just has degree 1 instead of degree 2. Okay, so the approximate degree can be smaller than the exact degree. Here's the key theorem relating quantum query complexity, bounded error quantum query complexity to approximate degree. Okay, so it says the following. If there is a T-query quantum algorithm that computes a function f, oops, I'm missing this should be -1 plus 1 to the n. Okay, so if there's a T-query quantum algorithm that computes f with error at most 1/3, then the 1/3 error approximate degree of f is at most 2 times t. Okay, So this was shown in a very famous paper of Beals et al., which introduced this polynomial method to quantum query complexity. So here's the archive reference for that paper. So a key idea in proving this theorem is to define a function p of x, where p of x is the probability that the algorithm on input x outputs 1. Okay, so a of x here is the output of the quantum algorithm on input x. Okay, so we know, because by this assumption that our quantum algorithm computes f with error at most 1/3, so therefore we know that if f of x is equal to 1, right, then the probability that a of x equals 1 has to be, so f of x equals 1, let's say, implies the probability that a of x equals 1 is greater than or equal to 2/3. Okay? On the other hand, if f of x equals 0, okay, so then this same probability has to be at most 1/3. Okay, so what that means is that this function p of x is actually a 1/3 error approximation of f. Okay, and so what we want to show is that if our algorithm A only makes t queries, then this polynomial here is actually going to have degree at most 2t. Okay, so that's the key idea for the proof. And the way that you prove this is basically by induction. Okay, so let's look at the state of the algorithm after t queries. Okay, so that some state. So on input x, the state of the algorithm after t queries is some state psi xt. Okay, and this is just a superposition of our basis vectors. Ket I, ket w. Remember again, ket. We have an input register and a workspace register. Okay, and I'm going to view the amplitudes on these basis states. I'm going to view that as a function of x. Okay, so therefore I can express these amplitudes as a polynomial in x. Okay, and we're basically going to show by induction that that these amplitudes are actually polynomials of degree at most t. Okay, so let's see why that's the case. So let's assume that this is true, and now we're going to advance the algorithm by one step and show that we get amplitudes that are polynomials of degree at most t plus 1. Okay, so if we now make a query, then the state becomes the following. Okay, so this is what's really nice about the phase oracle and working with the -1 plus 1 representation of the function. Right, so if the ith bit of the input is -1, then the oracle is going to multiply the phase of the corresponding state by -1. So actually and otherwise it just multiplies it by 1. So actually what we're doing is just multiplying by xi. Okay, so this is exactly our state after applying the oracle. And so you see that if alpha I comma w was a polynomial of degree t before, now it becomes a polynomial of degree t plus 1. Okay, at most t plus 1. Okay, so that's the first step to showing our induction. Now consider the case where we apply a unitary. Okay, so so now when we apply a unitary, well, what happens? So we arrive at some new state. Let's say now the amplitudes are beta IW, okay? And now these beta IWs, they're just going to be linear combinations of the alpha IWs, okay? But the degree does not increase, okay? Because, this unitary is, chosen at the start of the algorithm. It's completely independent of the input x, right? The only information that we get about the input x is through the oracle operations, the oracle queries. Okay, so actually this step does not increase the degree. Okay, so now we've seen by induction that doing one step of the algorithm, it can only increase the degree of our amplitudes here by at most 1. Okay. And furthermore, for the base case of the induction, you can see that, since we start out in this fixed state, this all zero state, so in that case, each the coefficients, the amplitudes are just polynomials of degree 0, right? They don't depend on x at all. This state is completely independent of x. Okay, so now we've actually shown by induction that after capital T queries, the state of the algorithm can be written in the following form, where each amplitude here is a polynomial of degree at most t. Okay, so now there's one thing left to do in the algorithm, and that's to make our measurement. The last step of the algorithm is to make this two-outcome projective measurement. And remember, at the very beginning of the proof, we defined the polynomial p of x to be the probability that the algorithm outputs 1 on input x. And this probability is exactly the projector pi1 applied to the final state of the algorithm, psi xt, the norm of that state squared. Okay, so, and we want to show that this p of x is a polynomial of degree at most 2 times t. So let's first think about the state inside the norm squared here. Okay, so pi1 applied to psi xt, that's going to be some state, sum over iw, beta iw of x iw. Okay, and these amplitudes, beta iw, they're still going to be polynomials of degree at most capital T. Okay, so this is just like the case we saw before when we apply a unitary. The unitary was independent of x. Likewise, these projective measurements, they're fixed by the algorithm and independent of any particular input x. Okay, so this does not increase the degree of these amplitude functions. Okay, and now we just take the norm squared of this state. Okay, so that's just going to be a sum over iw of beta iw of x norm squared. Okay, and now since each beta iw of x is a polynomial of degree at most capital T, this function, right, norm squared, will be a polynomial of degree at most 2 times t. Okay, and we have a sum of such polynomials. The result is again a polynomial of degree at most 2 times t. Okay, so that's the conclusion, that our polynomial p of x is has degree at most 2 times t, and that's what we wanted to show. Okay, so that is the polynomial method. We showed that if a quantum algorithm computes a function f, with error at most 1/3, and by making capital T many queries, then there is an approximating polynomial for f that has degree at most 2t. Okay, so what that means is that the 1/3 error quantum query complexity of f is at least the 1/3 error approximating degree of f divided by 2. Okay, so in other words, we can show lower bounds on quantum query complexity by showing lower bounds on this approximate degree. Okay, next we're going to see an example of how we can show lower bounds on approximating degree, and we're going to take as the example the OR function. Okay, so we're going to see that the 1/3 error approximating degree of the OR function is in bits is a constant times square root of n.